and this may seem, you may know this already, I don't know. But I think it's quite important. What I'm talking about is distinguishing between the different kinds of quantities in a model. So,
Okay.
so if we throw out some words here, parameters, inputs, state variables, independent variables. What else? There's one other group which not so important, I suppose, but absolute constants. Let me see, a quick check here. Just remind myself. Oh yeah, there's also outputs. Yeah, we also have outputs.
Are they FBML specific?
They're in SPML, but they may not necessarily call them these things. These words here are actually the words that are generally used in control theory. I mean, classical control theory, engineering control theory. Okay.
I see. Yep.
So, and I usually give it in class anyway with a simple example of a tank of water. Oops, let's do that properly. Oops, let's do that again. Ugh. Okay, so what we've got here, we've got 2 tanks of water, okay?
Yep.
They have a height. The water is a height h1, and this one is a height h2, and this one. There's a flow of water q1 coming into the tank, the first tank, and the units for q are volume per time. Okay, volume per time. And I've also got another flow coming in there to the second tank, and then this flow coming out here is that coming out of this pipe here is Q2, and the final flow coming out here is Q4. Okay, so we got 4 flows. All right. So the question is, what are all these things here that we have down here? So the first one, the easy one, is the inputs. Now, the inputs are generally those things that come from the outside, but which we control, all right? And we can control the amount of water coming into this tank and the amount of water coming into that tank. So the inputs, actually, let me put them here. So the inputs will be Q1 and Q2, sorry, Q3. Okay, those are the 2 inputs. So these are things that we control, okay? Now, there are other things which could be inputs, but which are not, which we don't treat them as inputs. For example, the diameter of the tank. I mean, in principle, I could go out and buy a new tank with a different diameter, but I'm not going to bother because it's too much effort. So for all intents and purposes, those are not inputs. And so, for example, the cross-sectional area, for example, is 1. These will be, that will be a parameter of the system. These are things that I could in principle change, but I'm not going to in this experiment. If I did decide to change them, they would then become inputs to the system. But because I'm not going to change them, they're parameters of the system. And another parameter, set of parameters, is the flow of water out of the tank. So we have to decide, you know, what determines Q2, for example, and Q4. Okay. This is where we have to, of course, invoke laws, some kind of physical laws that determines, or some empirical law that tells us how big Q2 and Q4 is. Now we know they must be functions of the height, okay, of water. I mean, clearly the higher the more water it is in the tank, the faster it probably comes out. We could invoke various laws. The really simple one, but wrong one, which we will use, is just that Q2, for example, is K, some constant K, times the height. So it's directly proportional to the height. That actually is strictly not true. It's actually proportional to the square root of the height, funnily enough. That's the nature of tanks of water. Now, this thing here is also a parameter. And there's also one attached to Q4 as well, but it's a different one for H2. Okay. These are things I could probably change if I got a drill out and drilled a bigger hole in the outlet pipe. Because presumably K is something to do with the size of the pipe coming out of the tank, right? So in principle, I could change the size of that outflow pipe, but I'm not going to. So I'm going to treat it in this model as a parameter, okay? So that's two parameters. The absolute constants will be things like the temperature, gravity. Temperature, I guess, is actually, temperature, I guess, could be a parameter, I guess, come to think of it. Yeah, let's make that, because I could easily change the temperature. So let's have that as a temperature. But gravity, I can't really easily change. So these are the absolute constants, okay? The independent variable, there's only one in this case, and that's time. Okay, because I'm going to be, this is obviously something running in time. I'm watching tanks fill up and empty and so on, so it's time. The state variables are the things, are the actual things, it's the smallest number. What's the definition of a state variable? What have I got here? State variable. Tell me, what is state variable? Okay. Oh yeah, dependent variables. These are basically the dependent variables. These are things that are inside the model that are changing in time, right? And they depend on time and everything else. And of these, there are two, H1 and H2, okay? And then the outputs, now the outputs are an interesting thing. In control theory, the outputs are some linear function of the state variables, in fact, because it turns out that in rail systems, we might not be able to measure all state variables. We might not have access to all state variables. This is certainly the case in biology, where you can only measure so many things, even though your model may have other things going on. And so the state variables include all possible dependent variables that you think are important in the model, but it's not necessarily the case that you can measure all of them. What you can measure are the outputs, okay? And so the outputs are generally a subset of the state variables, and also in general, there can be some linear combination of the state variables, okay? So we can write this whole thing down in a sort of a succinct form. Let me just write it down here. So let's, the state variables, by the way, are usually given the symbol xi. The intervariable is time. Don't bother with the output, absolute constant. The outputs are usually given the symbol y. The parameters, yeah, that's a tricky one, actually. Because often the distinction between the parameters and the inputs is often not made clear, and so the symbols for these two are often are often represented by the same symbol. So for now, I'll just call it P. Okay, for I don't know. Well, this is the problem, because I come from I've got my feet in two fields. So one field you calls them P, and another field calls them U, the inputs. And the parameters, they just don't even include them in the discussion. But anyway, so what we have we have the rate of change of the state variables is some function of the state variables and the inputs, which I'll then call U then, I suppose, here, okay? And then the outputs, yi, are some other function of xi and U. That's the general form. Now, when you linearize these, you will get this form. You could, no, let me not use that. Oops. So when you linearize these, which we haven't talked about, but linearizing, but when we linearize these, you end up with this equation. Okay, that one. And this one becomes yi equals dxi plus cu. Okay, these are the sort of general linear equations for any system like this, any system. These things here are usually matrices. Well, this actually turns out to be the Jacobian matrix, in fact. You can see here you have you can see here that the this piece here in particular shows you that the outputs are some linear function of the state variables. They may or may not have a U component. So that's basically what that they look like. And the control theorists love this stuff. They call these linear time invariant system, or LTI. You'll see this all over the place in control theory, because they love linear systems because linear systems can be solved, whereas these things cannot in general. Where these things can be solved, they can be solved. Right. So each of the components in these equations you can relate to these different kinds of things. So what have we got? Oh yeah, the parameters are things like area, K1, temperature, inputs are Q1, Q3, state variables are H1 and H2, independent variables time, absolute confidence constants such as gravity, outputs that is entirely up to us. For example, one output could be actually Q4. Sometimes, well, actually not sometimes, but often, I guess, the D matrix is just the I matrix, is just the identity matrix, and the C matrix is 0. So then you end up with yi equals xi. Okay, so in this case, that would be the case, because presumably we can measure both heights, h1 and h2, and there's no, the height is the height. I know I'm going to be using some ruler or something to measure the height, but there's a complete linear transformation from the actual height through the ruler to the number. So in actual fact, there's no distortion of h1 in any way by using a ruler, and in fact, in this case, the yi's equal the xi's. All right, but that's not always the case. All right. Not only that, we can measure both state variables, and so there's no. We have full information on this system actually. So, but in general, it's possible for this kind of thing to happen, and in fact, we do it in biology actually when we come to do fluxes. So actually, so is there any questions here? Because then what I'm going to do is I'm going to take this idea and then move it on to a kinetic model and show what the different parts are. Okay.
Yep.
All right. So let's have let's carry on using the X symbolism I use. So here's a pathway. Then I'll have X1 here, I guess. So I can have two boundary conditions. These are equivalent. This is sort of equivalent to Q1, effectively. All right.
Yep.
Or this rate, or the flow in anyway, is equivalent to Q1. So what are the? So let's look at the inputs. The inputs again are entirely up to me. So in this case, they were entirely up to me, and I chose that I had control over Q1 and Q3. I chose that, right? Okay, I chose that. So I'm going to choose that the input is X0. I'm also going to choose the enzyme E1, the enzyme E2, and the enzyme E3 as inputs, because I can control all those. X0 I can control presumably easily if it's in a chemostat or something. The enzymes I can control by changing the expression levels using CRISPR, whatever I want to do, okay? So those are the inputs then, X0, E1, E2, E3, okay? State variables, that's easy. X1 and X2, okay?
Yeah.
Parameters. excuse me, parameters, these will be the kinetic constants. So let's for the just sake of argument, v1 is k1 times x0, and one of the parameters will be k1. That's something that is extremely hard to change. That is highly unlikely to be an input in real life because I cannot change k1 easily. Conceptually, you can make it an input, right? You can live in, in a virtual world where you can pretend you can move k1, of course, but in reality, you can't. The outputs. Okay, that's an interesting one for these systems. There was an interesting, so Brian Ingalls, from University of Waterloo, so we have metabolic control analysis, which we haven't done, but there's a thing called metabolic control analysis, which was developed by a bunch of geneticists and biochemistry people. And then Brian Ingalls came along and realized that MCA, metabolic control analysis, was actually this. It was actually that, which we weren't aware of because we didn't know about the engineering control people at that time. But Brian is a control engineer, and he realized that what we did in metabolic control analysis was actually the same as what the control engineers do in control engineering. And he also realized that the outputs in metabolic control analysis, these things here, corresponded to the fluxes through the pathway. The state variables were the species. All right, so the outputs are actually the fluxes. So that, the rates, the steady state rates through the pathway. So what else have we got? Parameters, yeah, input, state variables, independent variables, time, still the same thing. Absolute constants, where we have those two. Yeah, the outputs became the fluxes. So that was really nice when he did that and linked the two fields completely together and showed that the outputs in classical control theory were the fluxes in metabolic control analysis. Anything else was the same. So we had the inputs, which was their u. We had the state variables, which was their x. And we had parameters and whatever symbol they use for parameters. Okay. And so now we would write down the differential equations we write then for dxi would be some function of xi and the inputs. Okay. And then the outputs in this case then were which we keep using y, was actually the fluxes, and the fluxes are computed from the reaction rates, okay, which are also a function of xi and u. So that was the equivalent formalism. This is the equivalent formalism that we would have if you compared it to what the engineers do. This piece here, okay.
See.
So and you can also write this piece then as well. This piece is easily written for a metabolic system as well. It turns out, as I said, this A matrix is actually the Jacobian. So that's what we get there. And I think yeah, go on.
Can I ask a question? So are all systems linearizable?
Yes, I would say so.
Okay. So it's in biology.
I mean, I'm talking about linearizing continuous systems based on differential equations.
Okay.
I don't know what happens if you have stochastic systems or anything like that. That's a whole other ball game. But if you have a set of differential equations, they're well-behaved differential equations, like there are no discontinuities, or there are no discontinuities in the region in which you're linearizing, and they don't go to infinity or anything, then you can linearize.
I see. Okay.
So as long as they will. So a linearization always occurs around a particular operating point. The idea of linearization is this. If you had, so this is x squared, okay?
Yeah.
Right? So this is nonlinear, Okay, now I can linearize this, but it's always a case of linearizing. You have to pick a point,
Mm.
and then you linearize. Basically, linearizing means discovering what the straight line would be at the tangent. What would be the tangent at that point? That's basically what linearizing means. So I could linearize some. Oops. No, no. I could linearize somewhere else, like here, and I would get a different tangent. All right. So linearization is a point specific operation. When you linearize at one point, it doesn't apply to the whole thing. It only applies to that particular place.
I see.
So in general, we in our models we always linearize around the steady state.
I see.
And then linearization basically comes from well, in this case it's this. So what's the slope of this line? The slope of this is called the slope m. Okay, so the slope of this line is let me call it y1 minus y0. So I'm going to call this y0 and then just drop this one down to x0. Okay, so if I take a line up, if I take a point up the straight line, I'll get y1. Okay. And that'll be my x1. So the slope is y1 minus the difference, all right, divided by the difference here, which is just x1 minus x0. So now what I can do is I can rearrange this so I get mx1. Let me see, hold on. Just want to yeah. Okay, hold on. Let me just do this for a minute. So what you use linearization for is to predict a new value of y, like y1, right?
Yep.
Given a value x1. Okay. So I want to know y1. So y1 equals yeah, y1 equals, I suppose I have to do it this way, I suppose, x1 minus x0 plus y0, okay? And then this piece here is the delta x. So y1 equals m delta x plus y0. So that's basically my linear equation. I can make it specific to a point by evaluating m. So let's say we were at x0 equals 4, okay? I know m is the slope, is actually dx squared by dx, okay, which is 2x, all right? But I'm at x0 equals 4, so m at x0 equals 2 times 4, which is 8, all right, which is 8. So y1 equals 8 delta x plus, and y0 is, y0 at x0 equals 4 is 16. So that's actually the linearized equation for x equals x squared at the point x0 equals 4. It'll be different at different points. But this number here and this number here will change. But I can use this now to predict a y1 given a delta x, you know, around x0 equals 4. So you do the differential equations are linearized in almost the same way, which is why you end up with this. Why this thing basically ends up as the Jacobian.
Yeah.
Okay. So, so anyway, I think this stuff is important because some people get confused. I've seen it quite a few times. Get confused about what the cause is or what the effect is. And it gets really complicated then when they're all confused and you can't talk to them. They haven't thought about it through properly, right? So in this situation, the inputs are the causes. I'm going to change E1, I'm going to change E2, I'm going to change X1, X0. The effects are then X1, X2, and the fluxes. These are the things I look at to see how they change. Sometimes it's very sloppy thinking I've seen in this, where they just mix them all up and it becomes nonsense. No idea what they're talking about. But it's really important, I think, to keep this very strict separation between the things you change and the things you observe as a result of those changes. So that's the reason why, and in metabolic control analysis, you make this distinction very clear, right?
Yep.
So, for example, it doesn't make any sense, right, to change X1 and observe the effect on X2, at least at steady state. It makes no sense at all, because X1 is a function of the system. You can't make it do something it doesn't want to do. So what will happen is, you know, if I try to, let's say I did that, right? I had time, I had X1 and X2, okay? And let's just plot X2. So there it is, X2, right? Then I inject some X1 in, right?
Oh.
So what will happen is X2 will start to rise and it'll fall back again, back to where it was before. No effect. So dx2 dx1 is 0. At steady state anyway, at least. So it doesn't make any sense to talk about how x2 is affected by x1. Because x1 is determined by the system, x2 is determined by the system. Collectively, they are determined by the system. They are not independent of each other. I mean, they're not. You can't talk about x0 as being an independent variable and x2 as being a dependent variable. It doesn't make any sense. They are dependent on, you know, the various inputs to the system. Now, of course, there are relationships between them, but they're only related to each other through the model. They're not related to each other independently. So. So in this case, yeah, the derivative will be 0, actually. So,
I see.
and people say these things, you know, how does x1 affect x2? Well, it doesn't. Yeah, there's a moment here where things happen, but then after a while, it doesn't happen anymore. It goes back to where it was. And so there was no net effect at all. But if I change the parameter, an input, there will be an effect, net effect.
Right.
Okay, I think that's it then for that one. Well, maybe, yeah, yeah. This is important. These are important points to be aware of, the distinction between, you know, what are the causes and what are the effects. I mean, yeah. So, any questions, or is that it then?
So, as in state variables, do you just like estimate parameters as well in real experiments?
In real experiments?
Yeah. Because in models, you generally...
Oh yeah, these things. Yeah, these things are generally unknown, right? Like the yeah, we might not know the diameter of the output pipe. Maybe we don't know the diameter of the tank because it's hidden behind a wall, and all we see is a little strip that tells us the height.
Yeah.
So there may be, yeah, there may be, these parameters may be unknown to us, but we know they exist.
Right.
And then it's up to us then to try to determine them by doing experiments. So this one, for example, this experiment here, we could actually use this experiment perhaps to actually do it as well. But normally what we would do, we'd have time 0 and we'd have x1, x2, and we'd probably start them at time 0, and then we watch them, you know, increase, you know, and change. So we'd have all these data points here in time, assuming this model is correct, right? And we have all the laws correct, we would be able to fit this data. So we'd be able to fit the model to the data, and that way estimate the parameter values.
I see.
But that's really problematic, though. I think. First of all, there's noise in the data, right?
Yeah.
And that adds noise to the final fitted parameters. That's okay. We accept that. But the biggest problem is knowing whether this is the right model. And if it's the wrong model, then who knows what you're getting. You'll get a fit maybe, but what does it mean? And so this is the big problem actually. I face and we all face in systems biology, and that is you fit your model to the data, but how reliable are predictions from that model if the model doesn't actually match what's actually going on? So what we've decided to do is that, and we're doing this now, is we've decided to generate thousands of model variants. And then we try to fit every one of them. And those that fit, we then say that's a plausible model. But there may be lots of them that fit. So we have lots of plausible models. And then the idea is, well, do two things. We can say our model is a collection of models, and the predictions come from the predictions that the entire ensemble makes. The other thing we can do is we can then ask the models, well, how can we distinguish between you by doing new experiments?
Right.
And then you try to whittle down the number of possible models. But the whole idea of truth starts to become fuzzy then, because will you ever know what the truth actually is? How much data do you need to get in order to state that you have the truth? Is it even worth talking about the truth anymore? At least at this stage, because it may be 100 years before you have enough data and whatnot to get actually what's going on. So my feelings about modeling has changed over the years. Now it's just I may not know what the truth is because I may not have enough time to find the truth, but I will be able to get models that are hopefully they represent some level of truth in what's going on, while at the same time they are useful, and at the same time they give me a mechanism by which to uncover a better truth about the problem. So that's the way I feel these days about models. And there is no one model. When you have limited data, it's silly really to talk about one model, because I bet you there's 1,000 others that are just as good.
Right.
So how can you talk about one model? There's a sort of a cloud of models that are consistent with your data.
Right.
So
Makes sense.
yeah. That's my position today. I mean, some things you can know with, almost certainty. For example, there is an enzyme E1, because if I remove it, the cell dies.
Right.
So I will assert a truth, that is, there is an enzyme E1. And the biochemists assure me that it does convert X0 to X1. So there'll be parts of my model which have high confidence, but there will be other parts which have very low confidence. And it's in those low confidence parts that we generate variance to try to capture the uncertainty and hope, yeah. Anyway, I keep meaning to write a paper on this, a perspective on this topic, actually.
Yeah, it's really interesting. So you end up getting like a set of models.
Yeah.
And work, but we never know which one is actually the correct one.
No. You may know in 100 years, maybe.
Maybe, yeah.
I mean, it's funny, I mean, Newtonian mechanics, they thought they had the truth. When it turned out to be, well, it's close to the truth, but not quite. So, and it goes on like that. The Greeks thought they understood the solar system with the sun going around the earth. Seemed to work, but it turned out not to be the case. So the idea of the truth is a bit fuzzy, really. You're sort of asymptotically approaching it.
Mm-hmm.
I think the two useful things about a model are, one, can it give you useful predictions?
Yep.
And two, is there a mechanism there that lets you improve the model? Gets you even closer to the truth. I think those are the two prerequisites. A good model has those two things. It can make some useful predictions, but it also provides a means by which you can improve it too.
Mm-hmm.
So, all right.
Yep.
We're good. Okay.
Thank you very much.
See you Thursday.
Yep. Bye-bye.
Bye.